Now we need to move on to the properties of light. As I mentioned earlier, much of what we understand about objects in space comes from understanding the light we receive from them. So we need a better sense of how light itself behaves. Let's start with a simple question. What is light? It sounds simple, but some of the biggest names in physics in the last few centuries have disagreed with each other on this one. One idea is that light is some sort of wave. One of the first people to do serious work on this was Christian Huygens, a contemporary of Isaac Newton. Another big name in understanding light waves was James Clerk Maxwell, one of the smartest physicists of the 19th century. He figured out that you could describe light mathematically from the equations that describe electricity and magnetism. On the other hand, it could be that light is a stream of some sort of particles. Isaac Newton was a big proponent of this idea. So was Albert Einstein. Einstein received his Nobel Prize for his work on understanding light as particles, not for relativity. So which idea is right? We'll look at both of these approaches and then see how the question was resolved in the early 20th century. Let's look at waves. A wave is a repeated disturbance that travels through a medium of some sort. We experience lots of different waves, and one of the key ways we define them is by what they move through. For example, there are sound waves. These are vibrations moving through the air. There are waves on the surface of the water. We can see those ones. There are waves that travel through the solid earth. We call those seismic waves, and they can be generated by earthquakes. There are waves that travel up and down on a stretched string. This can generate sound waves if the string is attached to a musical instrument. To a physicist, all of these are very similar phenomena with the same mathematics to describe them. Since all waves have a similar mathematical description, we can use a common language to describe all of them. Here are a few of the important terms we use to describe waves. The first one is wavelength. This is simply the distance between one peak and the next. Since it's a distance, it will have distance units, like meters. For example, water waves at the beach might have a wavelength of a few meters, meaning that one wave crest is a few meters in front of the next. Wavelength is one of the key ways of describing a wave. Consider sound waves, for example. A short wavelength sound is what we call a high pitch.
Something like this.
On the other hand, a long wavelength is a low pitch.
Like this.
Wavelengths are usually labeled with the Greek letter lambda, the thing that looks like an upside-down Y. The next term is frequency. We won't use that one much in this class, but you often hear it tied with wavelength. The frequency is how many times a second the wave passes a given point. A high frequency means many waves are passing each second. Going back to our example of waves at the beach, the big waves usually have a frequency of much less than one wave per second, since it's more than 1 second between wave crests. The third term we use is the speed of the wave. This is defined just like we did back in the last chapter. It's how fast the crest of the wave travels. However, we often use the letter c for wave speeds, as we've already seen for the speed of light. In the 19th century, James Clerk Maxwell showed that we could understand light as a wave in an electric or magnetic field. In other words, light is an electromagnetic wave. If you want to make a light wave, just take something with an electric charge and wiggle it up and down really fast. By Maxwell's time, there was already lots of experimental evidence that light behaves as waves. For example, it can bend around corners the same way a wave does, although the bending is very slight because the wavelengths are small. So how do you tell one wavelength of light from another? In other words, if pitch is what describes wavelengths of sound, what term do we use for wavelengths of light? Try to figure it out, and when you're ready, click forward for the answer. Different wavelengths of light are different colors of the rainbow. Red light is the longest wavelength of light we can see. It gets up to about 700 nanometers. Remember that a nanometer is a billionth of a meter, so even 700 nanometers is pretty tiny. Blue and violet light get down to 400 nanometers wavelength. All of the rest of the rainbow is between those extremes. Many colors we see are combinations of many different wavelengths of light. In particular, white light is a combination of all of the visible colors. This is why a prism can break light into colors. The colors are already there. They just haven't been separated out. A rainbow works the same way, with raindrops acting as prisms. This is a good point to come back to the speed of light. We've already mentioned that the speed of light is around 3 times 10 to the 8th meters per second. Here's the more precise number, though rounding it off the way we've done is plenty accurate enough for this class. This speed applies to light of all wavelengths, provided it is moving through a vacuum. If the light is moving through a material, it goes slower than this. How much slower depends on the material. Occasionally, we get asked if the speed of light is changing. As I mentioned back in the first chapter, this speed was first measured by Ole Romer back in the 17th century. Since that time, there have been no measurable changes in the speed of light in a vacuum. In addition, the speed of light is tied up with all sorts of important forces. So if the speed of light changed, it would profoundly affect things like the fundamental structure of atoms. However, we can observe galaxies and quasars that are literally billions of light years away, and hence we're seeing them as they looked billions of years ago. These objects show no sign that the matter has any different structure there than it does here and now. So the speed of light appears to be a very stable constant throughout the universe and far back in time. So what about the other picture of light, treating it as a stream of particles? In this approach, we treat light as being made of a stream of discrete bundles of energy called photons. Photons have no mass, they just carry energy, and they all move at the speed of light. The colors we see simply represent collections of photons with different energies. The bluer, shorter wavelengths are the photons with high energy, while the redder, long wavelengths are the low energies. As I mentioned, Albert Einstein received a Nobel Prize for showing that if you treat light as a stream of photons, you could explain why certain colors of light could cause electrons to be knocked out of atoms. This result eventually led to the technology of modern digital cameras and solar panels. By the early 20th century, there was a real conundrum developing around light. On the one hand, whenever folks did experiments to test if light was behaving as a wave, they found that, yes, it did behave as a wave. On the other hand, whenever they tested to see if light was behaving as a stream of particles, they found that, yes, it behaves as a stream of particles. This forced physicists into appreciating that there isn't an either-or answer here. Light is a wave, and it's a stream of particles at the same time. This was the beginning of the amazing world of quantum mechanics. We won't go into quantum mechanics much in this course, but it's important to understand that the things we consider to be common sense and natural on our size scale don't work on these very tiny scales, and a whole new understanding of common sense has to be developed here. For example, it's not just light that behaves as both particles and waves. Electrons and even whole atoms can do the same thing. In other words, we are just as much made of waves as we are particles. This may be why J.B.S. Haldane said in 1927 that the universe is not only queerer than we imagine, it's queerer than we can imagine. So far, we've been talking mostly about light with wavelengths between 400 and 700 nanometers. But what about outside of this range? In 1800, William Herschel did an experiment to measure the heat produced in different parts of a rainbow made by passing sunlight through a prism. Since he was a good experimenter, he put a thermometer outside of the rainbow to act as a control. He was surprised to find that the one outside of the rainbow got hottest. He had discovered a kind of light we couldn't see. Since it was beyond the red end of the spectrum, he called it infrared. The following year, John Ritter was also experimenting with this sort of rainbow, but he was shining it on a kind of light-sensitive chemical, a precursor to photography. He was surprised that the chemical reacted outside of the rainbow. Since this happened beyond the violet side, he called it ultraviolet. This was the beginning of our understanding that there are many kinds of light that we can't see. We call the full range of all forms of light of all wavelengths the electromagnetic spectrum. Here's a diagram of the electromagnetic spectrum. As you go to the right, you get to longer wavelengths or lower photon energies. Also notice the different types of light listed. On the far left, at the highest energies and the shortest wavelengths, we have gamma rays. As we move down in energy, we go through X-rays and ultraviolet light until we get to visible. Visible light, the only light we can see with our eyes, fits into that narrow little band between ultraviolet and infrared. You can see that they've expanded that section above the wavelength line just so that you can see the rainbow of colors. After we leave the red low energy side of visible light, we continue on through infrared and finally radio waves. All of these are light. They all move at the speed of light. They all can be treated as either waves or particles. The different names we give to the different parts of the spectrum have more to do with the history of how we've discovered them than anything inherent in the light itself. Light doesn't change fundamentally as you go from visible to ultraviolet to X-rays. We just made up those boundaries ourselves. However, as we will see, sometimes the way light and matter interact can change as you move to different parts of the spectrum. For example, ultraviolet photons have a little more energy than visible light photons. This means that when visible light photons hit your skin, they're simply absorbed and their energy is converted into heat. But ultraviolet photons have just enough more energy that when they hit your skin, they can start to break apart some of the molecules in the living tissue. If your skin is light-colored, it might turn darker to try to absorb this light before it gets deep enough to do any damage. The damage that UV photons do will cause sunburns right away and can lead to skin cancers over longer timescales. And yes, tanning booths do exactly the same thing to your skin as the sun's ultraviolet photons. You don't need to know the exact wavelengths or energies that mark the boundaries between different kinds of light. But you do need to know the order these types of light come in. Back in kindergarten, you might have learned a little song to help you remember the colors. Red, orange, yellow, green, blue, purple. Now that you're in college, you can extend that to gamma rays, X-rays, ultraviolet, visible, infrared, radio. So you should practice singing that to yourself to help you remember the sequence of electromagnetic radiation from shortest to longest wavelengths.